Okay, so now recording. So let me hand things over to group 13.5.
All right. Welcome to our senior design presentation. We are group 13.5. My name is Mackenzie and my teammates are Tessa, Sean, Drew, Caitlin, Atan, Varun, and Chris. We are all senior mechanical engineering majors at the University of Florida here to present our senior design project of a containerized satellite dispenser. I'm going to go ahead and pass the baton to Caitlin to present our overview of our presentation and products.
For our presentation, we will be giving a brief outline of our product, reviewing the market approach that has been driving our design, and taking a deeper look into the features and functionality of our subsystems and overall production costs. To give an overview of our design, we designed a canisterized satellite dispenser, also known as a CSD, to launch a 12U CubeSat into the moon's orbit. Our design is as depicted on the slide. The left image shows the exterior of the CSD, and the right image shows the interior. For our CSD, we divided it into 6 subsystems: the door and opening mechanism, the enclosure and CubeSat interface, ventilation and depressurization, launcher and interface, communication and power, and launch vehicle mounting. Next slide. And for our door and opening mechanism, we include a door with a latch, torsion springs at each hinge, and a linear solenoid and limit switch. And we have an animation with a red outline to show the specific parts. For our enclosure and CubeSat interface subsystem, we include carbon fiber side plates and aluminum 6061 front and back plates and door. This is well depicted by the left image, which shows the external facing parts of the CSD. And for our ventilation and depressurization system, we have ventilation grates and aluminum meshes at each chamfered corner of the CSD. For our launcher and interface subsystem, we include rails with rail foam and a spring attached to a launcher base plate and pusher plate that the CubeSat will sit on. For our communication and power subsystem, we have our electrical power system, EBIOS EPS, our CPU, Nanomind A3200, and an X-band antenna and transmitter as outlined in the red. For our launch vehicle mounting subsystem, we have M16 through holes on the back plate. Our product has the overall dimension of 292 by 309 by 446 millimeters. So it is able to fit in the payload fairing of any compatible launch vehicle. The overall mass is 4.97 kilograms, and this meets the customer's requirement of having the CSD under 5 kilograms. The internal dimensions are 226 by 0.3 by 226.3 by 366 millimeters, which is the capacity needed for us to fit a 12U CubeSat into our CSD. And now Mackenzie will be going over our market approach.
SatCube created a market approach to compete with competitors on the market. We are passionate about contributing to the future of space exploration. The CubeSat will be able to take high-quality photos of space, which will contribute to this goal. We wanted to be the best in the industry at optimizing the weight of a structurally sound system. This goal is at the forefront of our design. In later discussion of subsystems, the lightweight design will become apparent. Lastly, since money makes the world go round, our economic drive is delivering high quality product to sell to contractors. The buyer and their needs was at our top priority.
Okay, so the enclosure is the largest subsystem part-wise and comprises over a dozen parts, not including fasteners. It's based on an aluminum 6061 T6 alloy frame with Hexcel carbon fiber walls. Aluminum parts form the main structure of the CSD and take most of the load, while the carbon fiber plates serve to increase the rigidity of the frame. All the carbon fiber plates are coated in an AZ93 white thermal control paint, specifically designed for satellites and other spacecraft to reduce heat absorption and radiation. And to improve upon many of existing designs, our CSD enclosure features firm foam rails designed to attenuate vibrations imparted onto the CubeSat by the rocket during launch. Out of existing CSD designs listed in the CubeSat design specs, only 2 out of the 15 include a design choice that directly addresses vibrational attenuation. The foam we selected is a fluoroelastomer foam, which meets both the minimum and maximum temperatures expected during launch, and it meets NASA's requirements for outgassing. One major concern we had was ensuring the friction added by this foam would not negatively impact the launch system, and by specing a firm foam with an ultra smooth texture and a lubricant to match, this challenge was overcome. Next slide, please. For the enclosure to meet customer metrics, the CG must fall within the CG envelope prescribed by the SLS Mission Planner's Guide. And since our design is mostly symmetrical along the Z-axis, the CG is easily designed within the X and Y envelope. By careful weight reduction through milling at different points along the Z-axis, we were able to design the CG to be within the Z envelope as well. Next slide, please. One of the main aluminum parts that take the loads present during the launch, ascent, and orbit are the 8 rails that run the length of the CSD. During ascent, the maximum axial acceleration of the rocket expected is 4.1 Gs, and this is the largest acceleration expected at any point during the flight. Due to the mounting orientation of the CSD on the Z face, this axial load on the rocket translates to a longitudinal load on the CSD relative to its own axes, and this can be modeled as a simple beam. To complete these hand calcs, some assumptions had to be made. Firstly, the end of the beam is modeled as free, which isn't exactly accurate for design since this end is connected to the front plate and thus indirectly connected to the other rails. And secondly, the support angle bracket, which provides support at the midsection is omitted. So in this image, we have FCSD on the right, which is the weight of the door in the front plate, which is small, but with the moment arm, it is great. And on the center here, we have FCS, which is the weight of the CSD CubeSat of 25 kgs. Next slide, please. So on this slide, we show the cross section at the expected failure point was shown dashed on the previous slide, and using the parallel axis theorem, we can find the moment of inertia. Next slide. So here's just a table summarizing the intermediate values that we did to calculate this inertia. And we have the mass of the door, the mass of the front plate, mass of the CubeSat, and the forces this generates. So we're assuming that for the sake of these calculations that this force is divided among the 8 rails evenly, which again isn't necessarily completely accurate because it's not totally symmetric. So the goal of this is to provide rough estimates that we can do an FEA analysis for more thorough, exact calculations. Next slide, please. Based on the moments found in these forces, the combined moment of inertia and the distance of the stress concentration from the centroid, the maximum bending stress is found to be 48.6 megapascals. Then using the tensile yielding stress of aluminum 6061 T6 alloy, a factor of safety is found of 5.68. Next slide, please. And by simulating this exact loading scenario in SolidWorks, a minimum factor of safety is actually found to be 2.8 when probing and 2.3 overall, the overall being concentrated around one of the mounting holes at the bottom of the rail. It's important to note that this is an overestimation of the loading predicted and an underestimation of the support, because not only is the enclosure stronger as a whole, but the insertion of the CubeSat into the enclosure drastically increases the rigidity of the system. Additionally, the rail supports will provide much needed support at the beam's midsection, but even under worst loading, we still have factor of safety of 2.3. Next slide, please. And I'll hand this off. Yeah.
In order to perform thermal analyses on our CSD, we compare the expected absorbed solar radiation with and without the reflective coating we plan on using. The expected radiation absorption is a function of the solar absorbance of the surface that the radiation is incident on. So our radiation was roughly 1300 watts per meter squared without the coating and roughly 200 watts per meter squared with the coating. So we can see that the use of the coating results in an 84% reduction in heat transfer due to solar radiation. I'm going to hand things off to Tessa to talk about vibrations.
So the vibration in the launch vehicle is transmitted through to the CSD through the mounting interface. The launch vehicle's guides state that global vehicle motion drives excitations for frequencies up to 100 Hertz. For us, this means that vibrational loads are transmitted through the solid mounting interface up to 100 Hertz. Given this, the natural frequency of our structure should be outside of 100 Hertz. And in order to derive a natural frequency of the CSD can be modeled as a cantilever beam. The rigidity of the beam, or of a beam in general, can be derived as a function of the material's elastic modulus, cross-sectional area, and length. The main structural components along the length of the CSD are the aluminum rails or rail bars and the carbon fiber outer plates. The rail bars have a non-constant cross-section, and thus the minimum and maximum areas were found to account for both extremes in these calculations. Next slide, please. The carbon fiber plating and rail bars' independent rigidities can be combined as 2 parallel springs. For parallel springs, the equivalent spring constant is simply the sum of all the springs in parallel. The equivalent rigidities for each rail bar condition are shown at the right of the table. Next slide, please. The equation for the natural frequency requires spring constant and mass. The mass was taken to be 30 grams to account for the mass of the CSD with the of the 5 kilogram CSD with a 25 kilogram CubeSat housed within. As shown in the table, the structure's natural frequencies for both assumptions of area fall out of the 100 hertz far out of the 100 hertz range, and thus resonance due to excitation from the launch vehicle interface would not occur. Further testing would be required to attain more detailed information on the dynamic response modes of the overall structure. Next slide, please. And here's just a brief summary and overview of how the enclosure meets the prescribed customer needs. Next slide, please. The door and launching subsystems work in conjunction with each other. These subsystems consist of a spring-based launcher plate, spring-based launcher with a plate that aligns with the rails of the CSD seen on the left, and a door attached to the front plate of the CSD with two sprung hinges that are held closed by a linear solenoid. The launcher is held in compression when loaded with a CubeSat and when the door is closed. Next slide, please. The door locking mechanism relies on a linear pole solenoid attached to the inside of the front plate. When armed, as seen in the image, the shaft of the solenoid is fitted through a hole in the tab fitted to the door. The solenoid will retract itself when a current is applied, thus beginning the dispensing process of the CubeSat. A limit switch, seen in black, is positioned opposite the solenoid such that the status of the door opening can be monitored by onboard systems. Next slide, please. Here's just an overview of how the door subsystem directly meets prescribed customer needs. Next, please. The launcher spring took several iterations to converge onto our final design. These calculations were based around a combination of the upper limit of the exit velocity requirements and upper limit of the CubeSat mass. Aiming for the worst case energy requirement in this case would ensure that the spring is sufficient for all allowable CubeSat masses below 25 kilograms. We can also assume that the spring would be displaced from neutral by the length of the 12U CubeSat in the Z direction, which is the 0.366 meters displacement seen. A simple energy balance can be created between the kinetic energy of the CubeSat when it leaves the CSD and the spring potential energy of the spring when it is compressed by the CubeSat. From this energy balance, we can see that the required spring constant was solved as 746.514 newtons per meter. Next slide. These are the final base parameters of the spring designed for our CubeSat or our CSD. Other relevant spring properties can be calculated from these values. 302 in stainless steel in particular was chosen for its ability to withstand large temperature ranges when formed into wire without cracking. Next slide, please. The table in orange shows all of the calculated parameters based on those aforementioned parameters seen in the blue table. The actual spring rate increased slightly due to rounding the number of active coils to an attainable number. Also, the solid length of the spring was an integral part of reducing our design's weight, as it defined the lower bound for how much overall length of the CSD was necessary. It can be seen that the shear yield strength of the 302 stainless wire at 5.5 millimeter diameter and the shear stress of the spring at maximum compression resulted in a final factor of safety in the spring against yielding of 1.208. Next slide, please. Here's just a brief overview of how the launcher subsystem meets our customer needs. Next slide, please.
And now on to launch vehicle mounting. The CSD has universal launch vehicle compatibility and features 6 M16 through holes on the back plate as shown. It is capable of mounting on the Z plane of the upper stage of any approved launch vehicle. It is secured by mounting screws that are equipped with Loctite AbleStick 104, which meets NASA outgassing requirements of less than 1% of total mass lost. The launch vehicle mounting subsystem features screws that are capable of withstanding the maximum axial and bending forces applied by the 5 kilogram CSD and the 25 kilogram CubeSat at 4.1 Gs. Change slide. The screws are made of alloy steel, which have a tensile strength of 110,000 PSI. Several screws will also experience the force from the spring, since it will remain compressed until the box is open. This force F spring was used to determine the maximum force the screws will experience. To determine how much force a single screw can handle before yielding, the yield strength of the screws were used to determine the maximum axial force. Here, A is the minimum area of the screw, since it will fail at the smallest area first. However, since there are multiple screws with different diameters and varying yield strengths, the force was calculated for all fasteners to ensure safe launching of the CubeSat. The CSD mounting system is capable of handling all supporting loads generated prior to, during, and after launch, and in turn preventing the CSD from coming loose and ensuring mission success. Next slide. This slide just shows how the subsystem met customer needs.
Okay, so for the communication and power subsystem, there are 6 components. So we have the EPS, which is the electrical power system. We have the CPU, which is basically our computing unit. We have an X-band transmitter, which transmit the. We have an X-band patch antenna, which receives signal through the X-band network, and then we have the X-band transmitter, which can receive the signal which is received by the antenna, and also can send signal through the antenna. Then we also have the limit switch, which is part of the door, and we have the solenoid, which helps locking the door. Next slide. So our CSD is designed. We're expecting to receive 28 volts from the launch vehicle. So we use an EPS to step down the voltage and provide the correct voltage to each of the components. So the reason we have a computer is so that we can send commands to the solenoid, and we can receive signal from the limit switch. We can also send commands to the transmitter and receive the data from the transmitter too. Next slide. So this is a really simple communication and power schematic that I made. So first, you can see that the launch vehicle supplies 28 volts of the EPS, and then it is seen that the EPS is connected to the solenoid, the CPU, and the X-band transmitter. So as you can see, that the EPS steps down the voltage and provides the correct voltage to each of the components. Okay, so first, the EPS. So first, I'm going to explain the CPU. So the CPU is also directly connected to the limit switch, and as seen from the red arrows, the limit switch also sends signal back to the CPU. So what this is for is to make sure we know when the door is open and closed. So the X-band transmitter is also connected to the X-band patch antenna, which receives signal and can send signal and can send data through NASA's deep space X-band network. So it's also seen that the red arrows between the CPU and the X-band transmitter indicate that there's direct wiring between the CPU and X-band transmitter as well, because the CPU needs to send commands to the X-band transmitter and also needs to receive data from the X-band transmitter. So the EPS is also directly connected to the solenoid, but as you can see, the CPU, the dashed red line from the CPU to the solenoid represents that the CPU does send commands to the solenoid, but it does not have any direct wiring. This is because the CPU can send signal to this EPS to stop providing the voltage to the solenoid. And what this does is the solenoid can open once there's no voltage applied. It also must be stated that we have a simple grounding system as well. So we have used a threaded screw, which is screwed through the base plate of the CSD, and then the grounding from the EPS is connected to it. Next slide. So this is a simple, this is an overview of the communication and power customer needs mapping. Next slide. And this is our ventilation and depressurization system. So our system comprises of two components. It has an aluminum mesh, and it has another carbon fiber plate over it. So what the aluminum mesh does is it prevents small debris from entering the CSD, because the opening of the aluminum mesh is around 70 micrometers. So that is we picked a very fine mesh to make sure that there is airflow, but also it prevents debris from entering the CSD. So the reason we have another carbon plate over the mesh is because the mesh provides very limited structural rigidity. So what we did on the carbon fiber plate is that we drilled holes, so it doesn't render the aluminum mesh useless, and it also prevents bigger particles from. It's also one of the reasons for preventing the bigger particles from entering the CubeSat. So there are 4 of these, which are located along the length of the chamfered edges around the CSD box. And also what this system does is it prevents the need for specific depressurization system, because there's never going to be any pressure difference from the inside of CSD and outside of CSD. So we don't need a sort of seal or a valve or a vacuum to depressurize the CSD. Next slide. So this is also an overview of the customer needs mapping for the ventilation and depressurization system.
Moving on to production costs. To calculate total production costs, we've considered manufacturing costs, raw materials, assembly labor, and engineering labor. The manufacturing cost was obtained from the process costing table with multipliers for specific materials that needed to be machined. And the off-the-shelf units came from vetted suppliers, including McMaster Carr and AAC ClydeSpace. We've done this calculation for 1 unit production, a scale run of 100 units, and a prototype for testing. Next slide. Here we can see the cost breakdown of the manufacturing and material costs for a single unit and production scale run. Our single unit cost is around $48,800, and the cost for a production scale run of 100 units would be around $4.8 million. We were able to save some money on the production run because of bulk orders of material and fasteners, but the majority of the cost of the unit comes from the space grade electrical components used for communication and controlling other components like the solenoid. Next slide. Moving on to the prototype cost, the prototype will mainly be used for testing the launcher and door mechanisms, along with the thermal and vibrational loads that would be experienced during launch and the mission. Because of this, the expensive electrical components for communication are not needed and can be left out, along with changing some fasteners to lower cost alternatives. The rest of the prototype is identical to the CSD, using the same materials and dimensions to give accurate testing results. Another benefit to using the same materials for a prototype is that the electrical components can be added after testing to build a production unit to save on costs in the future. The manufacturing cost for a prototype unit is around $3,500. Next slide. For labor costs, we considered the design engineers and the assemblers. Engineers were paid the equivalent of a $75,000 salary for 6 months of work, and the assemblers were paid $19 an hour for the 12.74 hours of assembly time. This assembly time was determined using the Boothroyd and Dewhurst manual handling and insertion times for each step of the assembly process. The total labor cost for the engineers comes to $300,000, and for the assemblers, $242.06. Next slide. Adding these values for total cost for a single unit is $349,000. And for a scaled production run of 100 units, it's around $5.1 million. For the prototype, including some assembly, the total cost would be $3,800. Now you'll hear from Itan.
So there are some defining factors that our design brings that make it a viable option to be considered for prototyping. The simplicity of our design contributes to its manufacturability and ease of assembly. Since we only have two major moving components, the chance of failure due to unforeseen circumstances is quite low. Our design is also relatively unique in that our prototype uses materials found in our final design. This allows us to run testing on our prototype to perform structural, vibrational, and thermal analyses that should be representative of the loads that our final design will be able to withstand. All the custom parts for our design could be easily manufactured in Gainesville. This would cut down on time allotted to waiting for shipping on parts. Additionally, given that our total production cost is well within budget, if any unforeseen costs or issues arise during production, they could be handled without any concern for monetary costs. Our design is also relatively unique in that we have an onboard CPU and X-band transmitter, so the CSD can be totally self-sufficient in its communication with ground control on Earth and not have to rely on transmissions from the actual launch vehicle. CSDs currently on the market typically do not have these features. Our CSD also features integrated vibration attenuation of the CubeSat via foam rails. This feature, again, is not typical for CSDs currently on the market. Lastly, another defining feature of our CSD is that it is roughly 5 kilograms, which is about 0.6 kilograms less than the next lightest CSD currently available on the market, which gives it just an edge in just transportability and structural loads and things of that nature. Next slide. So yeah, if you would like to stay updated on any progress we make over at SatCubed, please follow us on Twitter. This concludes our presentation. Thank you all for attending today, and we would love to hear any feedback you have to offer.
All right, excellent. Let's hand things over to our panelists and see if anybody has questions.
Remind me again what the customer budget limit was on this project?
It was specified as $500,000 for the total cost, including design, testing, production, manufacture.
Okay, and then remind me again, what was your total cost?
I don't have the
For-
number on hand.
I've got it for you. For the one unit, it was $349,058.
Okay, so you stayed within budget. Good job.
Thank you.
Thank you.
Sorry, I'm trying to find it. Okay, there we go.
There it is. Okay, awesome. Good job, guys. It's the only comment I had so far.
Thank you.
Thank you, April.
Yeah, no problem.
Do you guys have any ability to vary your launch speed since it's a function of the compression of the spring, like the change in height? Do you have any ability to change so it can launch faster or slower if in the future NASA or whoever wants that in their project?
So actually our idea was to actually change the spring based on the mission requirements, because so that's the reason why we have we allow one of our side panels to be easily screwed and unscrewed, so we can take it out and switch the spring.
Okay.
But the reason we didn't add a specific system to vary the speed is because we felt like our main goal, like a very important goal of ours, was to stay under 5 kilograms. And that would have added extra weight to the CSD.
Okay, other questions from our panel?
Talking about I guess the weight on the top of your lid, there's like some X pattern. Was that just in there to like get down on weight, or was it just like a visual thing to make the lid look different? Like, why was the lid not just like flat on the top with the hinge?
That X
door?
pattern, or sorry, I'll answer this one. That X pattern was because of weight requirements. When
Okay.
we first designed our initial design, without including several other features, was already at like 5 kilograms. So we had to very quickly find places where mass was not explicitly necessary that could be milled out, and the door was one of the more obvious ones. And we also did confirm that it is still strong enough to withstand the loads that it would be subject to.
Yeah, in the presentation, I only went through the rail bar analysis for the sake of brevity, but in our full reports, we break down every single part is proven to be strong enough. We specifically reduced weight in regions where we could, where essentially the material would have been wasted if it was there.
Okay, any other questions from April or Alexander? Okay, well, let me ask a couple here, because I think we said we go until 5, so we've got about 13 minutes left. I might have missed it. Do you guys have a venting system that allows you to keep your pressure equalized with what's going on outside?
Yes, that's why we use that's why we have an aluminum mesh, so we can keep out debris while also maintaining a zero pressure difference between the inside of the CSD and outside.
Okay,
Yeah, all the edges were perforated, drilled through carbon fiber with the aluminum mesh underneath. So there's never really any significant pressure differential between the CSD and outside of it.
got
It's on
it.
all 4 chamfered edges.
Got it. So not using like a check valve or anything like that, but just like perforations with a mesh.
Yeah,
Yes, because
passive pressure control effectively.
Yeah. Okay. Did you guys encounter, and I might be getting the acronym wrong. I think it's MERV, and I don't actually know what the acronym stands for, but it's basically a ratio, and this is a NASA thing that I just learned this week. It's a ratio between the internal volume of whatever it is you're trying to vent, and then the cross-sectional area of your venting orifices. I don't know if you guys found that. There were a couple other groups that encountered it and used it to design the size of those vent ports.
we have not, but we based it off the smallest available aluminum mesh filter we could find.
Okay, got it. So the size of those holes is based on like an OTS mesh filter, and you just picked the one that was the smallest.
Right.
So okay, yeah, which actually I think, well, so this MERV ratio is a ratio of, I mentioned it, it's the internal volume divided by the port ratio, and it I don't know where NASA got this number from. I've got to dig more into it to see where it came from, but the number cannot exceed 5,000 centimeters, which is sort of unusual. It has units of length because it's a volume over an area, but it's sort of like the Reynolds number in a way, right? Reynolds number is dimensionless, but it's the ratio at which you're not getting sort of any weird like decompression effects inside whatever chamber you're trying to vent. And like I said, I have no idea where NASA gets the number from or how they derive it, but anyway, okay. So it might be, you guys might need to hunt that down and see if you're under 5,000. You can imagine it's again a ratio of volume to area. So as the area of your vent ports goes down, that number goes up, and once it exceeds 5,000, then all of a sudden you get into this danger of kind of the venting doesn't happen in a way that protects all the internal components from like really high changes in pressure over short periods of time. So that's one thing to maybe track down if you have time. My other question is, do you guys have, do you know what the steady state temperature is inside the CSD? Basically, the temperature for the CubeSat while you guys are both on the ground, waiting to launching, and then, in orbit before you deploy the CSD?
So we have a temperature range given to us from the SLS doc. that we were kind of basing our expected temperatures on. But in terms of finding an actual final temperature value, we were going to do that via testing, just due to the complexity of the thermal circuit we would need to account for all the conductive and convection coefficients that are going to be present, both like pre-launch, during launch, and once it's in orbit.
Yeah. Okay. So tell me about this testing, right? Because you can't actually, strap a CubeSat onto a launch vehicle and launch it. Well, I mean, I guess you could, but that would be quite expensive in terms of testing. So how do you guys plan to do the testing that you described?
I think we were going to kind of isolate conduction and well, we figured out radiation, we can calculate that. And as far as testing conduction and convection, we were kind of gonna just assume that the conduction was through our base plate and assume, I guess, both the worst, like the highest and lowest temperature that are going to be that the launch vehicle is going to achieve, which again, we got from the SLS doc. And then as far as convection, we were going to, again, base the air temperatures based on the SLS stock, and we could do some calculations and figure out a Reynolds number and kind of figure out what the convection is going to look like from there. So that could all be handled like in a lab, as long as we could control the temperature of like a simple metal plate.
Got it. Okay. Yeah.
So
Yeah.
we have, sorry.
No, go ahead. I was just agreeing. Go ahead.
So we can we also can run FEA and simulations, which can give us an idea based on the ambient conditions of the payload. But that one reason, we also made sure that all the components we're using are rated for that temperature range that we are going to use, and actually even a larger temperature range just in case. So we will definitely not have any issues with any steady state temperatures. Even the electrical components, they're rated for even lower temperatures than the temperatures we're going to expect.
Okay. How do you guys open your door? I know you guys talked through this, but are you relying on the satellite to push the door open, or do you guys have a separate mechanism to open the door? And when I say open, I don't mean unlatch. I mean actually physically open the door.
Yes, or
You can get it if you want.
okay.
You can go.
So
Yeah.
Fighting over.
The door is both, as you acknowledged, forced by the just spring of the CubeSat pushing on it, but also in the two hinges on the top of the CSD, there are torsional springs that are preloaded when the door is in its closed position. So in those two sets of springs in conjunction would ensure that as soon as the solenoid is released, the door would open and move out of the way of the CubeSat so that it can eject itself.
Okay, so if there were not that you would ever do this, but if there were no CubeSat in there, the door would open on its own once you unlatched it.
Correct. There's
Got
still
it.
springs in
Okay.
the hinges.
But I think I heard you say that the CubeSat is also pushed up against the door in the beginning, as in there's no, like the door itself is the arrest mechanism that prevents the CubeSat from moving. So how much force is on the CubeSat? Because you guys have got a spring, right, that pushes it out. So
Yes.
you've got that spring all the way compressed, and the CubeSat is basically pushing up against the spring on one side and then pushing up against the door on the other side. So are you gonna crush the CubeSat like an accordion, or did you interact with the aero team to make sure that it can handle that amount of force?
We were unable to get specific details from the aero team, but the intention was that the spring force would primarily be applied along the rails at all four corners. As that tends to be the main structural support from the CSD to the CubeSat. And yeah, did you have were you also asking about something with the door, or was it more with the?
Well, no, I just
Well-
we oh, sorry, did somebody
We did a similar analysis for the screws. with the tensile force, but we didn't do one for the CubeSat.
Yeah, I never did one directly for the CubeSat. The X launcher pusher plate is designed, like the pusher plate itself is designed with feet at the four corners. That way the force is transmitted primarily onto the rails itself. And I also performed analyses in our full report. I didn't include in here because it got too long, but on the back plate itself from the spring force to make sure that's able to sustain it. And we also did one on the door latch and the front face plate to ensure that the spring force, when it's compressed, will not cause any parts on our CSD to fail.
Okay, when you say force on the rails for the CubeSat, that's the rails on the corners of the CubeSat that interface with your rails,
Yep.
which presumably are the most rigid part of the CubeSat. So, okay.
Correct.
Yeah, well, so, I know, what do we have left? Like 6 hours, right, before the submission deadline. And I don't know if you could track that down in the next 6 hours, but that would be a good, if you've got the time and the bandwidth, just to make sure that you're not, you guys, you see what I'm saying, right? Is in, you've got the spring and it's in basically its maximum force configuration. And then the CubeSat is pushed up against the door. And so the spring is going to be pushing on the CubeSat, which is pushing on the door, which is closed. And then will the CubeSat buckle under that force? That's what I'm getting at. It sounds like probably not because of what you said with the force concentrated on the rails. But that there have been a couple of other teams that have struggled with that, which is why I'm asking. Okay. Let's see, you guys are opening the door separately. Is there any danger? Ran into this with the aero teams too. So when you guys did your TIM, your technical interchange meeting, I think one of the things that almost none of the groups discussed was like if the CubeSat is pushing against the door, even not to totally open it, but even just partially to help open it, does that pushing on the door end up knocking the CubeSat off of its desired trajectory? Do you guys have a sense of how much force the CubeSat is putting on the door versus how much the springs are contributing? And is the force on the CubeSat enough that it's going to get knocked off of its path?
The specifics of the force balance on the springs in the hinges versus that imparted by the CubeSat are not, I don't currently have them. However, the intent was that the torsion springs in the hinges would aid in opening the door fast enough that even when the door is mostly open, the CubeSat would still be mostly aligned within the rails, such that the forces transmitted between them as it gets to like parallel with the CubeSat would basically not affect it. And to that extent, the original excuse me, what is it? One of the initial designs of a CubeSat dispenser does operate on the same principle of the spring being held purely by the force of the door being held closed. So it was assumed that it wouldn't be an issue given the proportion of length to like width.
Yeah, okay, I got you. Oh, I had another question and it's just on the tip of my tongue. I'm gonna forget it now. Give me 1 second to see if I can remember it. No, it's gone. I'll remember it in a second. Let's see. So while I'm trying to think of the last question that I forgot, Alex or April, is there anything else that you guys wanted to ask?
At one point they had this beam analysis where it was free at one end,
Oh,
but
yeah.
then they
okay.
said that it wasn't free at one end.
So in the beam analysis, I modeled it as free at one end because it is mounted on the Z face and it's like a beam. However, it's really connected to the faceplate and linked to 8 other rails, but linking it to the faceplate and then trying to use the geometry of the faceplate to distribute the forces to the 7 other rails rather. became too complex for hand calculations. So I simplified it as free, and I took it as a worst case scenario where if it was connected to the other rails and it had the angle bracket, it would be stronger. And it was still able to withstand the force at worst case, worst acceleration, and worst support possible. So that's why the hand calculations. That's why I ran the FEA after to model it more accurately, because I was able to do it by hand in a succinct manner.
Yeah, the FEA analysis is probably a better thing to present than just
Yeah.
free.
Yeah, the FEA, I just wanted to justify at least the principle of it
Mhm.
before I ran into the computer simulation without any kind of basis for what the beam was. But I agree the FEA is definitely much more accurate.
Yeah, and just to be fair, we give them kind of a warning about Tom Singer from Northrop Grumman, who has a reputation of if you show him an FEA without hand calcs to back it up, he spends the entire session ripping apart your FEA. So that might be, since Tom's not here, might have been overkill to do both the FEA and the hand calc, but I understand why you did it, because you wouldn't have been able to show the FEA without the hand calc, or Tom would have jumped all over you had he been here. So yeah, so good sort of being aware of your audience, and
Definitely consider
adjusting.
that.
Yeah, adjusting
That's why.
accordingly. I remembered my question, which goes back to what Tessa was saying about the speed of the satellite coming out versus the door opening. And there's actually two questions there. So first is, I think you guys did this, but anyway, I'll ask. Do you guys have the calculation for the speed at which the door opens, like the dynamics for that? And can you prove with math that the door actually does in fact open faster than the satellite gets popped out?
We do have those calculations based on the torsional spring constant and the angle of deflection and whatnot. I don't have them on hand. I would have to dig for the specifics of that. I think we did confirm that it would.
We did, but it's in the report. I'll try to find it.
Oh, no, that's okay. Just
No,
so long as you
but-
did it is what
Yeah.
I'm asking. So, okay. So that's one. And then two, the spring, again, when it's totally compressed, that's the maximum force that the CubeSat experiences, at least when it's in the CSD. What sort of acceleration is it experiencing right in that moment when it launches? And is that acceleration enough to cause damage?
You were saying the acceleration that the CubeSat would be subject to?
Yeah. So I'm talking like F equals MA, right? So like the door, let's just imagine that the door swings open before the CubeSat even moves, right? So now you've got a oh, okay. Thanks, Alex. Sorry, Alex is
Thank you.
just dropping
Thank
into
you.
chat a message that he's gotta go. So the door swings all the way open, and now the CubeSat is sitting there. The spring is totally compressed, and the CubeSat is sort of looking out into space, and it's like, okay, I'm gonna launch now, right? And then what it experiences is the maximum force of the spring in that moment before it starts moving. So like what's the acceleration on the CubeSat, and is that large enough to cause damage?
So
Sorry.
I literally went to my slide that has the maximum force of the spring when it's compressed by the CubeSat, and I took that force and divided it by 25 kilograms, and that would be 10.94 meters per second squared, so a little
Okay.
over a G.
Okay.
So assuming it's fine on Earth and through launch, it should probably survive being pushed out.
Great.
Yeah, launch be at 4.1. So as long as it can withstand that, it should be fine. And Aero did advise us that they wanted the highest velocity possible specifically, and they would be able to sustain it. They actually wanted higher than 2. We couldn't do that because the spring force just got too great. But their structure, they said, was perfectly strong enough to sustain this.
Okay, perfect. Yeah, just wanted to check that you guys did that. We have had a couple of groups that they did all the static calculations and everything was fine, and then when they did F equals MA, they were up to like 5 or 6 Gs because they had like super stiff springs. So okay, just wanted to check that you guys did that. Sounds like you did. Oh, and I'm looking at the time and realizing that I said we would stop at 5 and it's actually 5:05. So and we've lost Alexander. April's still here, but probably a good time to wrap up. April, if you've got one more question, we've got maybe time for one more quick one.
No, I don't have anything, but you guys did great.
Thank you.
April.
Thank
Thank
you.
Thank you.
Thank you.
Yeah.
Okay, well, very good. All right, then let's wrap up there. So I just want to thank you guys one last time for sharing your presentation with us this evening. I think you guys are maybe the last or the second to last group to go. So, last but not least, and I also want to, say, like this was an unusual group, right? In that you enrolled in kind of the weird section, right? The online section. And then we had that even weirder situation where halfway through we had to combine two groups into one. So you guys had to deal with kind of a lot of like administrative baggage that the other groups didn't have to deal with. So I appreciate your patience. Your patience with me for the course of the semester, and your persistence and grit, and kind of bringing it all together with energy and creativity to get to this point, which I think is a really excellent design. I'm really impressed with the outcome. So just want to thank you guys for a great semester, and hopefully you enjoyed taking the class as much as I enjoyed teaching it. So
Thank you,
It was
Professor.
tough, but we
Yes,
really
thank you so
enjoyed it.
much.
Yeah,
Thank
thank
you.
you so
Thanks.
much. I
Very
really
fulfilling.
appreciate your guidance.
Thank you.
Yeah, good job,
Thank
guys.
you.
very good. Yeah, and April says good job. So that's coming from April. She's one of the tough ones. So it means a lot.
So now.
Tough ones, yeah.
Anyway, let me stop recording.